Hi, my name is Adu-Bredu. I present here today our work on optimal constraint task planning as mixed integer programming. In this work, we propose GTP MIP as an approach for optimal constraint task planning. Given a task with symbolic and continuous goals and constraints, GTP MIP outputs a grounded plan made up of a logically consistent sequence of actions with optimal continuous parameter values. So this is the composition of GTP MIP. So the first component of GTP MIP is the hybrid PDDL description, which is an optimal constraint task description we propose in this work that describes optimal constraint task planning problems. Next, we pass this task representation as a hybrid funnel graph. And then after building the hybrid funnel graph, we encode both the hybrid funnel graph and the hybrid PDDL description as the mixed integer convex program, which we then solve to obtain a logically consistent sequence of actions, each with its corresponding optimal continuous parameters. And this action sequence is then executed by the robots. Next few slides would go into detail. We'll give a detailed description of all of the components. So the first component we look at is the hybrid PDDL description. So the hybrid PDDL description is an extension of the PDDL language for describing optimal constraint task planning problems. And it's made up of two files. The first file is the domain.hpd file. And the second file is the problem.hpd file. So the domain.hpd file essentially describes all the available action primitives. And here's an example of the domain.hpd file. So an action primitive here is the pick action. The pick action has a number of fields. The first field is the parameters field, which describes all the parameters of the action. The second is a precondition field, which describes a conjunction of all the symbolic preconditions needed to be satisfied in order for the action primitive to be executed. The second field is the continuous precondition field, which describes all the continuous preconditions that need to be satisfied. The next is the dynamics field, which describes the dynamics function of the action. And the next field is the continuous effect field, which describes the end values of the continuous parameters after the action is executed. Finally, we have the effects field, which describes the conjunction of all the symbolic effects after the action is executed. The next file required to describe our optimal constraint task planning problem is the problem.hpd file. So this file essentially describes the actual problem we're trying to solve. So it has the init field. So it describes the initial symbolic propositions, the goal symbolic proposition, the initial continuous variable values, and the goal continuous variable values, as well as the external constraints and the objective function to be optimized. The next component of GTP MIP is the hybrid funnel graph. So the hybrid funnel graph is a concise representation of the plan space. And before we delve deep into the hybrid funnel graph, let's take a detour to figure out what exactly funnels are. So consider an action primitive that has sort of continuous preconditions that are constraints that need to be satisfied in order for the action primitive to be executed. So these continuous preconditions are represented by these constraints. And so here I'm showing a number of linear constraints that represents the continuous preconditions of a specific action. And so the intersection of all of these constraints results in a convex hull, which we call the input region. And it's made up of a list of all of these inequality constraints. Next, we have the action dynamics, which is a dynamics function that essentially tells us the values of the continuous variables after the action is executed. And it's often represented as an ordinary differential equation. So the dynamics function is applied to the extreme points of the convex hull of the input region to form another convex hull, which we call the output region, which represents the region of all the continuous variables after the action is executed. So this gives a funnel shape. This results in a funnel shape, and that's why we call it funnel. And the funnel is a versatile representation of hybrid actions. And hybrid actions are actions that can have both discrete and continuous preconditions and effects. So given this representation of actions as funnels, we then build a hybrid funnel graph. So at some time step level t, we have a state level, and a state level is a set of all the symbolic propositions at that level, as well as all of the continuous regions that represent the possible regions or possible values of the continuous variables. The set of all of these represents the state level. Next, we compute applicable actions, and applicable funnels are the actions that can be executed at level t. And an applicable action is an action whose symbolic preconditions are satisfied in state level t, and whose continuous variables or continuous variable regions intersects the continuous variable regions in state level t. So represent these funnels as shown. And funnels with a filled circle representing the output region are funnels that do not result in any continuous effects, or whose effects are purely symbolic and non-continuous. We also have another type of funnels, a different type of funnel which are identity funnels, and we call them the no-op funnels. So these funnels represent identity operations, that's actions that do not make any change to the states. And so these funnels have the same preconditions and effects, symbolic preconditions and symbolic effects. So having computed all of these applicable funnels, we then build the next state level. The next state level is made up of the collection of the symbolic effects of all of the applicable funnels, as well as collection of the output regions of all the applicable funnels in level t. So these output regions are computed by applying the action dynamics on the region of intersection between the input region of the funnel in action level t, funnel in level t, and the continuous regions in state level t. So after building the state level, we then check if the symbolic goal propositions are satisfied by the symbolic propositions in the state level t+1, and if the continuous continuous goal variable regions intersects the continuous regions in state level t+1. If these two conditions are satisfied, then we are done building our hybrid funnel graph, and then we terminate the building process. But if not, we use the same process as we described before to compute all the applicable funnels and keep building the graph till it terminates, until we reach till the goal conditions are satisfied. So that represents the hybrid funnel graph. So the next component in our approach is the encoding of the hybrid funnel graph and the hybrid PDDL description as a mixed integer convex program. So mixed integer programs are mathematical programs, or mathematical optimization problems with both integer and real value variables. And having this quality makes them advantageous in modeling hybrid decision-making problems like task and motion planning problems that must make both discrete and continuous decisions. So the HFG and the HPG are encoded into a giant MICP, which is shown below. So this MICP is made up of an objective to be optimized. And this objective is usually a convex objective to be optimized. For the Warehouseman problem we consider in the paper, this objective is essentially to minimize the Euclidean distance the road moves. And this objective is subject to constraints like the initial symbolic constraints, the goal symbolic constraints, the precondition constraints, the effect constraints, the mutual exclusion constraints, the external constraints, then the initial constraints, initial continuous constraints, and the goal continuous constraints. And the variables involved in this mixed integer program are the integer variables p and q, which can take values of 0 and 1, and the x continuous variables, which live in the special Euclidean space. So by solving this single giant mixed integer program, we end up with a sequence of logically consistent actions, each with optimal continuous parameter values, which can then be executed by the robots. So we move on to experiments. So the first experiment we run is to compare the symbolic planning capabilities of GTP MIP with the state-of-the-art symbolic planning approaches. And so you notice from the results that for the first 4 problems, GTP MIP plans much faster than fast downward or Piper plan. And so for small problems, GTP MIP is quite fast. But once the problem size increases in problem 5, you realize that GTP MIP spends significantly more time than all the other planners. And this is essentially because once the problem size starts to get bigger and bigger, the number of variables, both discrete and continuous, and the number of constraints in the resulting MICP gets really large. And as a result, solving the corresponding MICP problem takes a longer time. So GTP MIP doesn't scale well on pure symbolic planning problems. However, this is not a problem because the main advantage GTP MIP has over all of these pure symbolic planning approaches is that it's capable of solving optimal constraint task planning problems, or problems with numeric constraints and numeric objective functions. And all of the other approaches that are compared to it here do not have this capability. So that makes GTP MIP quite special. And we further evaluate this numerical capabilities of GTP MIP on this Warehouseman problem. So in this problem, we provide GTP-MIP with an optimal constraint task planning problem description in form of an HPD file, which has a set of constraints, goal constraints, external constraints that need to be satisfied. And these constraints are constraints on the block placement poses or the package placement poses in this Warehouseman's problem. And we see from the results that GTP-MIP is able to at least satisfy all of these constraints and solve this symbolic and solve this optimal constraint task planning problem. Numerical results from this run can be found in the paper. Finally, we apply GTP-MIP on real-world mobile manipulation problems on a humanoid robot. So the task here is to store a cookie box on the second pane of the shelf. And the constraints, the numerical constraints here, which are essentially continuous precondition constraints in action primitives, are robot stance constraints and stable grasp constraints. So the robot stance constraint basically is basically a constraint that constrains the robot's stance pose to be such that it can reach the objects to be picked, or it can reach the placement pose of the objects. And the stable grasp constraints is a constraint on the grasp used to pick up or place the object, such that it satisfies some definition of stability, grasp stability. And in this way, it's essentially that the robot grasps the objects at a 45-degree angle. And this makes it much stable when the robot walks while moving the object. And it's worth noting that in all of these experimental runs on the humanoid robots, we use the default proprietary whole body controllers that are provided by the robot manufacturers. So here's a video of the shelf stocking task. So first, the robot adjusts itself and approaches the table to satisfy the stance constraints. It then picks up the box while satisfying the stable grasp constraints. Having carried the box, it approaches the shelf and adjusts itself to satisfy the stance constraints. Finally, it places the box on the shelf while satisfying the stable grasp constraints, the stable placement grasp constraints. And we have more video experiments, more video runs of the robots performing other mobile manipulation tasks on the project webpage. And the link to the project webpage can be found in the paper. Thank you very much.